All right, so in this video I'd like to try to do some comparison between ellipses and hyperbolas, and thereby sort of introduce the hyperbola as sort of an inside-out ellipse. So on both sides here I've drawn a box, and the box has a center at hk in both cases, and then it has one dimension is length 2a, with a being the half width, and the other dimension is length 2b. B being the half height or something like that. So for an ellipse, you have I'm going to use purple. And for the ellipse, you have your foci inside the box at an equal distance from the center. So I'm going to put a focus like here and another focus here. So same distance away on either side. And then this distance to the center would be the value C. Right, so now we have A, B, and C. And then using that geometric definition that points on the curve measured back to the foci added together equals 2A, you get this very nice ellipse curve. Try to draw a decent ellipse here. Well, okay, it's messy on the right side, but you get the idea. So the ellipse is formed inside of the rectangle, right? With passing through all four of those points, but otherwise it's kind of curving around inside the rectangle. It just sits right there with the rectangle around it, okay? So that is with the foci on the inside. You get the equation. You get that equation, and you also have the relationship c squared is a squared minus b squared. So we've got that. Now for the hyperbola, things are a little different. With the hyperbola, we talk about the foci being outside of the rectangle instead of inside the rectangle. So let's say I put the foci here and here. Now my c value is that distance on each side. So C is now bigger than A, like that. And if C is bigger than A, then things are a little different. You can't have the distance back to the C adding up to 2A any longer because the string would be too short. Like see, the string would be too short to connect to the foci, right? So that doesn't make any sense any longer. We have to change the definition, and instead of talking about adding the distances to the points, instead of like, back here with sticking a point on this curve and saying take that distance and then take that distance, the two distances to the foci, and adding them and setting them equal to a constant. Instead, with a hyperbola, you're talking about taking the distances. Let's take about a point like here, for example. Distances to the foci, you take a difference of those, subtract them from one another, and set that equal to a constant, which would be 2a again. And you end up getting this, actually no, sorry, not right there. You end up getting this nice curve that has two parts, one part over there and another part over here, like that. So this curve, you would have a similar setup with the x minus h squared and the y minus k squared, right? So for the center, the shifts put you centered here. You're still dividing. In this case, a is horizontal, so you're still dividing by a squared here and dividing by b squared here. Except instead of added together, you now have them subtracted, and that equals 1. So that was all in red. That is what's called a horizontally oriented hyperbola. But with this exact same setup, you could also put the foci, instead of putting them on the horizontal axis, you could put your foci on the vertical axis, still outside the box right here, and end up with a different hyperbola, which is oriented vertically, with its foci on the outside here and passing through those points. So that one looks a little different. You have to swap the order of these two terms and put the y term first. Whichever term, this is our x term and this is our y term. Whichever one is positive tells you the orientation. So if the x term is the positive one, it's horizontal. If the y term is the positive one, like this, so just taking these and swapping the order, then that is the vertical orientation. That's in green. So we call this vertical, and with this one, whoops, horizontal. So with any particular A-B choice, you can kind of orient your thing vertically or horizontally and make two different hyperbolas by swapping the orders there. In either case, there's a relationship like we had over here with c squared is a squared minus b squared for an ellipse. It turns out that changes for a hyperbola, and we get c squared is a squared plus b squared for a hyperbola. So yeah, so everything kind of changes. It's like you're swapping the pluses and minuses around everywhere, right? Like in the ellipse equation, you're adding the terms, but then the a squared minus b squared is subtracted. And in the hyperbola case, you're subtracting the terms, and the a squared and b squared are added. So those both kind of swap around. It's a nice, easy way to remember it. Yeah, and I think that's all I wanted to say. Oh, there's one more thing I wanted to say about these, which is that hyperbolas have diagonal asymptotes. So I'm going to come through here and draw these diagonal asymptotes. So there's one, and there's the other. And these diagonal asymptotes pass through the center of the box and the corners of the box. So these corner points here, 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 and here. If you draw those asymptotes, that can be a really nice guide. Actually, I should have drawn the asymptotes first, because that gives you a nice guide for drawing the hyperbola. They're going to pass through points called the vertices. These points are called the vertices. They'll pass through those points on the box, but then they will sort of approach the asymptotes on either side. Yeah, that can be a helpful guideline when graphing a hyperbola. And the slopes of those asymptotes, by the way, are always going to be given by the a and the b. It's rise over run, right? So this is like up b over a. So b over a. And then the other one would be down b over a, so negative b over a for those two slopes. I think that's about all I wanted to go over in this video. I think I'll do an example, and that'll do it for hyperbolas.